Okay, welcome back. So this week we're going to talk about troubleshooting deep neural networks. And just to place you for a second in where we are in kind of the life cycle of a machine learning project, so where we are in the course. So we talked a couple of weeks ago about planning and project setup. We also talked about infrastructure and tooling last week. We haven't talked about data collection and labeling yet, but we will talk about that soon. But this part of the course becomes relevant like once you've collected your initial data set, you've labeled it, and now you're moving on to training models and debugging those models as you go. And so why this is a class on like applied machine learning in some sense, right? Like putting deep learning models into production. So why have a whole lecture on training and debugging and troubleshooting? I think this XKCD comic kind of captures what it feels like a lot of times to actually build a machine learning system, right? So you're pouring a big pile of data into a pile and you're stirring it around and some answers come out the other side. And if the answers are wrong, then just keep stirring and maybe the answers will turn out better. And I think this kind of captures what it feels like a lot of times to iterate on machine learning systems. I also like this tweet from Andre, which, first it doesn't even compile and then it doesn't link, then it seg faults and then it gives the wrong answer. And then only after all that, then maybe it actually works. And so this I think captures a common sentiment that I hear among practitioners, even really, really top tier practitioners, which is that it's when I first started in the field, I felt like I was doing something wrong because I was spending 80% of my time or 90% of my time, debugging things and tuning models and stuff like that. But it turns out that that's, even some of the top people in the field, this is kind of how they spend their time as well. And the goal of this lecture is not to try to eliminate the time that you're going to inevitably spend debugging and tuning your models, but hopefully to give you some strategies so it feels a little bit less like you're like just spinning this random pile of linear algebra and waiting for better answers to come out of the other side. Okay, so the first thing I want to talk about is I want to just give you some intuition about why this is such a hard problem, right? Why are top practitioners spending so much of their time troubleshooting models? So I'll use an example. This is a chart from the original ResNet paper. And suppose that you're trying to reproduce this chart, right? This learning curve. And let's say that your learning curve actually looks like this, right? So, you're doing significantly worse than the model in the paper is doing. And, and so the question is like, what do you do after that, right? So you've implemented the model, it's not doing as well as it does in the paper. What's going on? Why is it not doing as well? And so the insight here about why troubleshooting is so hard is that there's a bunch of different things actually that could be causing the same dip in performance. So you could have an implementation bug. And to make matters worse, most deep learning bugs are actually completely invisible, right? So I once had a bug that looks something like this, right? So, my model just wasn't training at all. This is one of the snippets of code, or a caricature of one of the snippets of code that I was using to train the model. And there's a bug here. Any ideas what that bug might be? Paste it in chat or chime in if you know. Okay, so no one else knows this bug either. Yeah, so Nathan got it. The order is random. So it turns out that when you call glob in Python, the ordering that it returns files in is not deterministic. And so I didn't realize this. I had this bug. My model wasn't learning anything at all, and it took me like half a day or a day or something just to even find that this is the place that I had it. But implementation bugs are not the only possible source of the same error. So it could also be caused by hyperparameter choices. And it turns out in deep learning, oftentimes our models are pretty sensitive to small differences in choices in hyperparameters. So this is kind of a cartoon chart about what can happen to your model's performance if you choose different learning rates. Right? So the difference between a good learning rate and a low learning rate might not be that big, but if you have a high learning rate or a very high learning rate, your model might might not get to as good an answer at all, or might actually just not learn anything. Like the signal might go in the wrong direction. And this is a chart from I think this is a follow-on to the ResNet paper, talking about where they actually, one of the tricks that made this paper work at all was the weight initialization. And so the difference between what was the standard weight initialization at the time and the weight initialization that they used in this paper was the difference between the model not learning anything at all and the model being state of the art. on the tasks that they were working on. So models can be extremely sensitive to the small differences and choices of hyperparameters that you might make. Another cause of possible poor performance is what I would call like data model fit. So maybe the data in the paper that you're trying to reproduce is ImageNet, let's say, and yours could be something else, like let's say it's self-driving car images. And if you're re-implementing the same model using a different data set than was used in the paper, then it's reasonable to believe that your model should also perform well on your data set, but there's no guarantees of that. And so using data that's really different from the data in the paper could be the cause of degradation in performance. And then lastly, the way the data set itself is constructed can also cause degradations in performance. And so this is, I think, a pretty commonly shown chart at this point, but this is from a talk that Andrej Karpathy gave not too long after he had taken over the reins at Tesla and after he had left OpenAI. And the insight here is that, I guess the chart is a little fuzzy in this picture, but the insight is that when you're working on your PhD, when you're working on research, then the vast majority of your time is spent thinking about models and algorithms, not data sets. But in industry, in the real world, it's actually flipped. Like most of your time is spent thinking about data sets, and models and algorithms are actually a small portion of that. And I think actually even this characterization that 25% of your time maybe is spent on models and algorithms is probably much lower in places other than Tesla. And there's a bunch of different things that could cause data set construction issues that affect model performance. So maybe you don't have enough data. Maybe you have enough data, but the classes are very imbalanced. So you have some classes that are dramatically underrepresented. Maybe your labeling process itself could be noisy. So your labelers could be giving you incorrect labels. Your train and test set could be from different distributions, or any number of other different data set construction errors. So to summarize, why is it hard to troubleshoot the performance of your deep learning model? Well, it's hard to tell that you actually have a bug to begin with. And even if you have a bug, even if you know that you have a bug, so you're lucky enough to know that you have a bug, there's a lot of different possible sources of the same degradation in performance. And so it can be hard to disambiguate which cause is actually causing that degradation in performance. And then lastly, models can be very sensitive to small changes in your hyperparameters and how your data sets are constructed. And so those are sort of some of the main reasons why it's hard to troubleshoot models once you're building them. And so the bulk of what we're going to talk about today is a strategy that you can use to overcome this. So a strategy for troubleshooting neural networks. And yeah, I think that maybe if there's one takeaway that you have from this is that I think there's one key mindset that you need to keep in mind as you're building your models that is going to be one of the biggest sort of differences between being able to build models successfully or kind of getting stuck in the endless cycle of lots of bugs. And that's the mindset is pessimism. Okay, so the key idea that I advocate for in troubleshooting models is since it can be really, really hard to disambiguate what is the cause of this degradation in performance, what is the cause of this error, the strategy that we're going to take is we're going to start with something that's as simple as possible, and then we're gradually going to ramp up the complexity so that at each step along the way, we're only increasing the complexity by a little bit. And so if performance doesn't behave as well as we expect, or the way that we expect, then we can isolate that small change that we made as the degradation in performance or the unusual performance that we weren't expecting. And we can start our debugging there. Okay, so in a little bit more detail, the strategy that we're going to talk through is, starting very simple. So choosing a simple model, simple data set, and really paring down your problem to the essential components of it. Then you're going to implement that model that you chose, and you're going to debug your implementation. Once you have an implementation that you're reasonably certain is bug-free, then you're going to evaluate your model. And you'll use the results of that evaluation to make a decision about what to do next. So it could be, improving the model or improving the data, or it could be tuning your hyperparameters. And we'll talk about how to make that decision and what the different ways that you can improve your models and tune your hyperparameters are. And then you're going to iterate on this process, kind of looping back to the implementation phase or the evaluation phase until you have a model that meets the requirements that you set out at the beginning of this exercise. So really just to summarize all the stuff that we're going to cover, starting simple, you're going to choose the simplest model and simplest data possible. Then when you're implementing and debugging, you're going to first get your model to run. Then you're going to overfit a single batch of data. So just one batch, a few data points. and then you're going to try to reproduce a known result. In evaluation, the strategy that we're going to take here is we're going to apply the bias variance decomposition, and we're going to use the results of that to decide what to do next. For hyperparameter tuning, the strategy that we'll recommend here is doing course-defined random searches. We'll talk about a couple of other strategies you can consider. And then finally, if you're improving your model and data, the kind of number one strategies that we'll recommend are to simply make your model bigger if you're underfitting, and add data or add regularization if you're overfitting. But we'll talk about other possible strategies as well. Okay, a few things that we are going to assume that you already have in place before you start going about this process. The first is you need to have an initial test set, so an initial data set that you're going to use to perform your model evaluation. We'll also assume that you have a single metric to improve on. So we talked a couple weeks ago about how to choose, what metric you are going to work on improving at any given time. And then we're also going to assume that you have a baseline, right? So some target performance that's based on, maybe human level performance, or some paper that you're trying to reproduce, or a previous baseline, or maybe some requirements. And again, we talked a couple weeks ago about how to pick a good baseline. And so for the sake of example today, we're going to use this running example. So we're going to use a running example of pedestrian classification. So suppose that we're working on building a self-driving car, and as one component of that, we're training a model that takes as input an image of a scene and tries to classify whether or not there's a pedestrian in that image. And let's say, for the sake of example, that our goal here is going to be 99% classification accuracy. Okay, so some of you are going to go work on self-driving cars after you graduate, and I hope that you're aiming for higher accuracy than this. But for the sake of our example, let's say that we're targeting 99%. So basically, the rest of this lecture is we're going to walk through this strategy, and we're going to talk through some more details about how to implement each of these steps. So starting simple. All right, so the steps that we're going to talk about here are, first, we're going to choose a simple model architecture. And then we're going to pick some sensible defaults for that model architecture. Then we'll talk about normalizing inputs. And then finally, simplifying the problem itself. So I think architecture selection is something that causes people a lot of stress and worry especially when they start out in deep learning. And I think there's good reason for that. There's millions of papers out there, and there's a lot of different choices of architectures for different problems and subproblems, and there's many trade-offs between them. But the good thing is that when you're starting out on a new machine learning project, I think if you're working on something practical, then I think that there's some relatively simple pragmatic choices you can make for version 0, your first attempt at solving the problem. And so, the way I'll break it down is based on the type of data that you're working with. So if you're working with images, then I would recommend starting for the first implementation that you do with a Linnet-like architecture, and then over time, as you start to improve model performance and rule out bugs in different parts of your code base, then you can consider moving on to something like a ResNet. If you're working on sequences, then I think the recommendation that I typically make, at least as of a couple of years ago, was to start with the LSTM with a single hidden layer. I think maybe starting with the transformer now could be equally valid, if not more valid, recommendation. Although I think maybe a transformer is still a little bit harder to implement the first time. And then as your project gets more mature, you should consider moving to a transformer or a WaveNet-like model. And then if your data is anything else, then for version 0, I would recommend starting with just a simple, fully connected neural net with a single hidden layer. And then as you get more mature, then that's kind of when you need to pick something problem dependent, depending on exactly what you're working on. Okay, so you might say, well, this makes sense if I have just a single type of data as input. But what if, in the real world, oftentimes we have multimodal data. So how should you think about dealing with multiple input modalities? So say that you have a model that is taking, one or more images as input, as well as a sentence, and is trying to classify whether that sentence accurately describes the images. So the model architecture that I'm going to describe here as a baseline is, first you map each of the individual inputs down to a lower dimensional feature space using the architectures that we described before. So you might map each of the images through a small convnet, and you might map the sequence through an LSTM. Then you're going to take the output of each of those models and flatten it, concatenate each of those feature vectors, and then pass the output of that through one or more fully connected layers until you get to the output that you're trying to predict. Yeah, concatenate, good catch. And so this, very simple choice here, but can be a reasonably strong baseline for a lot of tasks where you're dealing with, multimodal input. It's simple to implement and relatively simple to debug. Okay, so we've chosen our simple model architecture. And the next thing that we're going to do is we're going to pick some sensible defaults for hyperparameters and things like that before we start training. So here are some defaults that I recommend using for version 0 of your model. I think it's best to start with Atom Optimizer. So some people recommend just starting with like vanilla SGD. I think Atom just like solves a lot of problems for you. So might as well use Atom. This is the learning rate I like to use. I think this is also popularized by Andre. I think it's in popular culture, it's known as the magic learning rate because it's more often than not gets you pretty close to the learning rate that you would have picked if you had done some hyperparameter optimization. For activations, I would start with ReLU or 10H if you're using LSTMs. These weight initialization schemes, which I'll define on the next slide, but I won't go into detail on. And then importantly, I would recommend in the first implementation that you do, not starting with any regularization or data normalization. And the reason for that is that regularization and data normalization, things like batch norm and stuff like that, are a very, very common source of bugs. And so I think, until you know that you need those things, I would leave them out of your implementation so you can make sure that the rest of your implementation is bug-free before you add something like batch norm. This slide just has the definitions of the recommended initializers. I won't cover this, but you can come back and look at it if you're interested. Okay, so we've chosen simple architecture, sensible defaults. The next thing that is really important to do, even in the first implementation, is to normalize your inputs. What does it mean to normalize your inputs? So for most data, this is just subtracting the mean and dividing by the variance. You're probably doing this already. For images, it's fine to just scale the values to something between 0 and 1 or negative 0.5 and 0.5. One kind of gotcha here is that sometimes your library will do this for you. And so I've had a lot of bugs where I divide the values of the input image by 255, but that was also happening somewhere else in my code. All of a sudden my input values are tiny. The model learns really slowly. So this is one step that I think that you should absolutely never skip because it can make the difference between your model learning normally and not learning anything at all, depending on the scale of your data. All right, so we've picked simple defaults for our problem, but I think one other thing that's really worth considering when you're starting out on a new problem is actually trying to simplify the problem itself and then gradually adding back the complexity that you need in order to solve the problem that you really want to solve. So a couple of examples of ways that you could do that. You can start with a much smaller training set, for example. So what this will allow you to do is it'll allow you to iterate more quickly, and it'll allow you to understand whether, if your model's not performing well in this data set, if that's because the data set is really challenging or if it's because there's a bug, right? So if you can't get your model to perform well on a smaller data set, then you're not going to be able to get it to perform well on the larger data set that you really care about, at least in terms of training error. You can also reduce the number of objects or classes that you're considering. You can decrease the image size or the size of your inputs in some other way. Or you could even consider using a simpler data set altogether. So you could create a synthetic training set. And we'll talk a little bit in labs about how you can think about doing that. Okay, so the way that we might approach this for our pedestrian detection problem is, we're a self-driving car company, so we actually have millions and millions of training images. But since we're just starting to work on this pedestrian detection problem, we'll start with a subset of 10,000 of those images for training. And it's a little cut off here, but 1,000 of them, let's say, for test. We'll use a simple Linnet architecture since we're doing classification. We'll use Atom Optimizer with the magic learning rate, and we'll leave all regularization out to start. Okay, and so this is just a quick summary of some of the techniques that you might use to start with the simplest possible version of the problem that you can. All right, so you've picked your simple architecture and defaults, and the next thing that you're going to do is you're going to go and implement that model and debug your implementation. All right, so the steps we're going to cover here are, first, you need to get your model to run at all, which sounds easy, but is not always as easy as it sounds. Then you're going to overfit a single batch of data. And once you can overfit a single batch of data, then we're going to compare the results of your model to some known result. All right, so to just give you a quick preview of some of the stuff that we're going to cover here, I think in my experience, these are 5 of the most common bugs that tend to come up when you're implementing a deep learning model. So one really common one is you have the wrong shapes for your tensors. So you're trying to add something that's like 3 by 4 together with something that's like 3 by 5. Usually usually this will fail loudly, which makes it relatively easy to debug, but it's also possible for it to fail silently, particularly in TensorFlow, where you'll have kind of accidental broadcasting when you have shapes that are undefined. And so this can be a silent source of bugs. It can be very, very painful to find. Pre-processing inputs incorrectly. So forgetting to normalize your inputs or over-normalizing your inputs is a pretty common source of bugs. One other thing that's like really easy to do by accident is to have the wrong input to your loss function. So a lot of times the loss function will expect just the raw logits of like from your model, but you'll take the softmax because that's logically what you want the input to be, and then you'll get bugs because of that. Forgetting to set up train mode for the net correctly. This again often comes up in batch norm. And then various different sources of numerical instability, which, if you're implementing new types of models, you'll inevitably spend a lot of time debugging. Before we go into specific strategies, there's a few pieces of sort of general advice that I have when you're implementing a new machine learning model. So the first is to start with as lightweight an implementation as you can. So adding the minimum possible new lines of code for version 1. And so intuitively, like the way to think about this is that every line of code that you write is like could possibly have some bugs in it. And so if you have fewer lines of code, your debugging process is going to be easier because there's going to be fewer places to look for the error. And as a rule of thumb, I think trying to get your implementation to something less than 200 lines for the first version is generally a good goal. And oftentimes, like I would really try to get things to be less than 100 lines, but it's not always possible to do that. And one other note here, this doesn't count like tested infrastructure components. So if you have like some infrastructure that you've been using for a lot of different models in your code base, then those are fine. Like don't count those toward your 200 lines. Another piece of advice is generally try to use off-the-shelf components when you can. So for example, Keras is great for implementing a first version of your model. Same with PyTorch Lightning, which we're using in the labs. Using the definitions of layers that are built into your library instead of writing out the math yourself, which can be tempting to do because you're trying to make a simple, lightweight implementation. But the implementations of layers and things like that in these libraries have a lot of the kind of numerical gotchas already taken care of, especially in the loss functions. And then lastly, and this is maybe actually the most important thing, is a lot of times we're working with massive data sets. And so in order to deal with those massive data sets, it's important to build kind of like complicated data pipelines that sort of shuttle all of the data from wherever it's stored to your GPU in an efficient way. But I would highly, highly recommend starting with a version of your data set that you can load into memory when you start working on a problem, and then building those complicated data pipelines later, because data pipelines are almost inevitable source of bugs. And so you want to make sure that your model implementation is working well before you add these in. Okay, now let's talk through the steps here. So the first thing that we're going to do is we're going to get the model to run. There's a few common issues that'll come up here. One is you might have a shape mismatch, or you might have a casting issue. So your model expects floats and you're giving it ints. And recommended resolution here is just step through the model creation in like your Python model implementation in a debugger, and just like inspect the shape and types of the outputs at each step until you get to the point where something is happening that's wrong. Out of memory issues are another really common source of bugs at this stage. And so what I like to do here is just look for all of the operations that are going to be memory intensive. So, creating large tensors, loading large blocks of data into memory, and just scale those back one by one. Like try reducing the batch size, try, making those, like the number of channels smaller or something like that until you get down to something that can actually run. And then and then that will tell you where the original like memory intensive operation might have been. And then many other things that can go wrong here. And so I recommend kind of the standard software engineering debugging toolkit, which is basically like Googling stuff until you find a plausible source of the error. Okay, so zooming in on this process of stepping through model creation and inference in a debugger, I think, for PyTorch, it's relatively easy to do this in something like IPDB. For TensorFlow, at least like older version, non-imperative version of TensorFlow can be trickier. And so I think like maybe none of you are really using non-imperative TensorFlow, but if you ever end up using it, one trick you can use is you can just step through the creation of the graph in a debugger. Another trick that you can do is you can actually step into the training loop itself and like evaluate tensors individually by just doing sesh.run in TensorFlow. And then lastly, there's a TensorFlow debugging tool that is worth taking a look at here if you ever end up in the unfortunate position of needing to do a lot of debugging of non-imperative TensorFlow. Okay, so to summarize, first thing that we're trying to do is get our model to run. And so we're dealing with shape mismatches, casting issues, out-of-memory issues, and then a whole litany of other things that can go wrong that we can try to start by Googling. All right, so I cover a couple of other kind of more detailed sources of bugs in these slides, like diving into a little bit what can cause shape mismatch and casting issues and things like that. I'm not going to go through those in detail right now, but they're here for you if you want to take a look later. All right, so we've implemented our model and now it's actually running. So we're done, right? Like we can write the paper, graduate, and it's all good. No, of course not. Like this, when you've got the model to run, that's actually where your debugging really starts. And so the next thing that I'd recommend doing is overfitting a single batch of data. And so what do I mean by this? Well, I mean literally a single batch. So 2 or 4 or 8 or 32 data points. And by overfitting, I mean driving the loss arbitrarily close to 0. So, if you get loss to go to some number that looks low to you, but then it kind of plateaus, it can be tempting to say, okay, yeah, we're overfitting a single batch of data, but that doesn't actually count. So what you really need to be able to do is pick some number and then make sure that the loss can get arbitrarily lower than that number. So arbitrarily close to 0. So what are the things that could go wrong when you're overfitting a single batch of data? Well, instead of driving the error down to 0, in some cases, the error will actually go up. And so if the error goes up, the most common thing is that you've flipped a sign somewhere. So maybe you're optimizing the negative of your loss function instead of your loss function. But there's other possible sources of that problem. The error can also explode. So it can go down for a while and then all of a sudden shoot up and then get arbitrarily high. And so if the error goes down and then up, usually in my experience, this is a numerical issue. And so you can check all of your operations that could be causing a numerical issue, but it can also be caused by the learning rate. The error can oscillate, so it can go down and then come back up and then go down and then come up. In my experience, this is often caused by corrupted data or labels. So, your learning problem might actually be impossible because, for example, your labels might be shuffled. That's I think the most common cause of error oscillation, but it can also be caused by a learning rate that's too high. And then lastly, your error can plateau. So the error goes down, down, down until you get to 0.1 or 0.01 or something like that. And then it doesn't really get much lower after that. And so I think the thing I would try here if you're getting a plateauing error is you can try to turn up the learning rate a little bit and getting rid of regularization if you didn't listen to my advice and you're using regularization in your first implementation. And if that doesn't work, then I would check I would kind of check very carefully your loss function itself, like how you're defining that, how you're computing it, and your data pipeline, because there could be bugs there as well. Okay, and this is just all this in one slide. All right, so once we're able to overfit a single batch, then the next thing that we should do before we start trying to make our model more complex or adding more data or anything like that is comparing the results that we're getting to some known result. And this is the last kind of sense check that we'll use to convince ourselves that our model is reasonably bug-free before we move on. So not all known results are created equal. I'm going to go through some possible known results that you can compare to, kind of in order of what I think their usefulness is. So I think the most useful thing, if you can find it, is some official implementation of the model that you're implementing evaluated on a data set that's like yours. And so the reason why this is so useful is because you can walk through both implementations line by line and ensure that you have the same output. And you can also make sure that your the performance that you reach in the end is on par with what you should expect your model to do on that data set. If you can't evaluate the official model implementation on your data set or a data set that's like yours, then you can try comparing to the implementation on a benchmark data set like MNIST. And so this still lets you walk through the code line by line, but the results, like the numbers that you're getting on MNIST, don't really tell you much about how well your model is actually doing, because pretty much everything does well on MNIST. If there's no official implementation of the model, you can instead use an unofficial implementation of the model, with the caveat that like I would be very, very careful if you go down this path, because I've found that like the vast majority of like random model implementations that you find on GitHub have pretty serious bugs in them. In fact, like even some of the official implementations of models have bugs in them. So just generally, I wouldn't trust other people's deep learning code too much unless it's kind of like a really well-established code base. If there's no implementations available, maybe the paper just came out, you can look, or maybe you made it up, you can look at the results from a paper without looking at the code, which will tell you whether your performance is roughly in line with what you'd expect, but won't help you figure out what's wrong if it's wrong. You can also look at the results of your model on some benchmark data set, right? So you can look at your model on how well your model performs on MNIST, and pretty safe to say that if it's not getting 99.95% or 99.5%, let's say, on MNIST, then there's probably some bug, because generally everything that's doing reasonably well should be above 99% on MNIST. If you don't even have that, then you can look at results from a similar model on a similar data set, or if nothing else, you should be looking at super simple baselines, like just the average of all of your outputs, or the result of running a linear regression on your data set. And this, if you don't have access to anything else, this is still useful to do, because you will catch bugs this way. There are examples, like I've had examples where your model is actually doing worse than just randomly predicting, or just like predicting the mean of all the labels in your data set. And so at the very least, this will tell you that your model is learning anything at all. All right, so in summary, how should you think about implementing and debugging your model once you've chosen your model architecture that you're going to use? So the first thing you need to do is get it to run at all. And some techniques you can use here are stepping through things in a debugger and watching out for shape, casting, and out-of-memory errors. Once your model runs, you need to overfit a single batch. And so if you can't overfit a single batch, that means you have a bug, and likely causes of bugs are corrupted data, or over-regularization, or maybe broadcasting errors, silent broadcasting errors. And then once your model can overfit a single batch, then you want to compare to a known result and keep iterating and looking for bugs until your model performs up to expectations.
Oh, go ahead.
Yeah, I wanted to ask, so like you talked a lot about creating an ML project from scratch. Like I'm curious, do you have any advice for people that are like going in and starting with an already somewhat like developing or developed ML system?
Yeah, I think that's more or less what the rest of the lecture will be about, like how to iterate once you have some starting point. But I would say, the same principles apply. You should like try to gradually increase complexity. So if you have an idea for a new model architecture, then maybe just change that and see how that changes performance, rather than like changing the model architecture and also like changing the data set and changing the like a bunch of other things as well. Or you can take that even one step further, and like if you have an idea for a new model architecture, then don't make all the changes you want to make all at once. Maybe if like one of the changes you want to make is like switch out your nonlinearity for some like fancy new nonlinearity from some paper that you read, and you also want to like add attention in a couple of places, and add like one or two other things as well, then like maybe just pick one of those to start, and then try it and see if that improves model performance before you go and implement like all four of those things.
Thanks.
So there's a question in the chat. What is IPDB versus PDB? I can answer it.
Yeah, can you answer it? Yeah.
PDB is the Python debugger, and then IPDB is the Python debugger. So it's just a little nicer. It has like syntax highlighting.
I think I've never used regular PDB before.
Yeah.
I don't know why you would. Maybe if you're like running on someone else's machine or something and you can't install stuff.
Yeah. Yeah, IPDB is nicer. And how many epochs should you expect to run in order to overfit a single batch?
Oh, it could be a lot. Yeah. I wouldn't necessarily like worry too much about the number of epochs, because your epochs are going to be really fast with a single batch. Like they should be very, very fast. If they're not very, very fast, then that could be some other source of bug. But I mean, really, I would expect this to take like less than a minute, probably.
I have a quick question, and I guess it's kind of like out of ignorance, but I kind of want to push back on the premise that overfitting a single batch is that useful. Like, I mean, I guess for some reasons, like if the batch is too big, then you won't be able to you won't be able to draw the error rate down to zero if your model is small enough. And I guess B, if there's some problem with the data, or like some fundamental noise in the data that you actually can't get, then I'm not sure you'll be able to draw it down to zero anyway. I'm just not sure what. Yeah.
The way I would think about it is, let's say that you have 32 data points in your batch and you have 32 parameters in your model, then you should be able to memorize the batch. So if you're using a really small model, then just make your batch size smaller. And I would say the reason why this is useful is like more an empirical observation than anything else, which is just that like most people I know who do this consistently frequently catch bugs doing it. And most people from personal experience, whenever I don't do it, there's like a 20% chance that I'll end up regretting it later because I'll spend a day working on something and thinking I have some really complicated bug, but then it turns out that I can't even overfit a single batch. So it's almost free to do this. Like it should take you like 5 minutes, and if it works, then you can just be more confident about the next step.
Do you recommend like visualizing your data, at least for like images in particular, I guess? Like, do you recommend doing some of that stuff before as a method of debugging, like doing visualization before and after, just to see if like something at least makes somewhat sense?
You mean if you're generating images or something like that?
Generating images, or maybe generating labels or bounding boxes. You just want to see like what the actual output looks like.
Yeah,
it's hard to.
Yeah, absolutely. We'll talk more about like kind of a general method for that in a bit. But yeah, I think inspecting your data before you get started is a really good idea. Like just playing around with it, trying to label it yourself, and just generally getting a feel for what the distribution of data looks like is not something that you'll regret, most likely. All right. So moving on to model evaluation. So the TLDR of evaluating your model is that we're going to apply the bias variance decomposition, and we're going to use that to make decisions about how we prioritize next steps that we take in sort of model creation or model, like generally the process of making your models better over time. So to review the bias variance decomposition. So let's say that we have some human level performance or some target performance in general, and then we have a loss curve, like our training error that's plotted in green here. Generally speaking, your validation curve will be another learning curve that is hopefully above your training error. Your test error will be yet another one that's above your validation error. And so the bias variance decomposition breaks down your test error into different components. So the first is the term of art is often irreducible error, which is some error that you don't expect your model to do better than. So if you have a really strong human baseline, then you could say that that's your irreducible error. And then you look at the difference between your irreducible error and your training error, and that's a measure of avoidable bias, right? So how much your model is underfitting to that training set. Then you can look at the difference between your validation error and your training error, and that's a measure of variance. So how much you're overfitting to your training set. And then finally, you can look at the difference between your test error and your validation error, when you do infrequently evaluate your model on the test set. And that difference is a measure of how much you're overfitting to the validation set. So to summarize, the bias variance decomposition says that your test error can be broken down into some irreducible error plus bias plus variance plus validation set overfitting. So one assumption that's baked into this is that this all assumes that your training, validation, and test set all come from the same data distribution. So what should you do if that's not the case? Which it's not the case in a lot of real-world machine learning problems. So for example, like if you're working on self-driving cars, then you might have a situation where most of your training data looks like the data on the left, right? So it's data from daytime driving scenes. But then in the real world, you also have to deal with data that looks like on the right. So let's say data that's at night. And the strategy that I'll recommend here is to actually use two validation sets. One that's sampled from your training distribution, and then a second that's sampled from your test distribution. And I think it's really important to do this even if you have very limited data from your test distribution. Because what this allows you to do is it allows you to add one more curve to this bias variance decomposition. So between your test error and your training error, instead of just having one validation error curve, instead you're gonna have two validation error curves. One that corresponds to the training validation set, the validation set you sampled from your training distribution, and then the other that corresponds to your test validation set. And so the way that this affects your bias variance decomposition is that in addition to underfitting, overfitting, and validation set overfitting, you also have this other term, which is the difference between your test val error and your train val error, which is a proxy for how much distribution shift is hurting your model performance. Okay, so let's look at an example of this strategy. So let's say that we train our first model, our like simple Linnet model, on this pedestrian classification task, and these are the numbers that we get. So our goal performance was 1%, and our training error is like really bad. It's 20%. Our validation error is even worse, and our test error is not too much worse than our validation error. So this difference between our training performance and our goal performance, this massive 19% difference, tells us that we're pretty seriously underfitting our training distribution, our training set. The difference between our validation error and our training error tells us that we're also overfitting at the same time, which is very possible to do with neural nets. And then the difference between our test error and our validation error is relatively small. So let's say for now that we're happy with this difference, like we're good here. And so the question here is like, we are both underfitting and we're overfitting. So what do we actually do? Like, how do we decide what to work on next? And that'll be what we cover in the next section. But for now, just to summarize, what I recommend doing here when you're deciding what to work on next in your model is breaking down your performance into some irreducible error, some bias, some variance, some distribution shift, and some validation set overfitting. And then the next thing that we're going to do is we're going to use those numbers to make a decision about what to implement next in your model. All right. So next, we're going to talk about how to actually make improvements to your model and your data to try to improve model performance. And so the way that we're going to apply the bias variance decomposition to prioritize improvements is we're going to follow the following set of steps. So the first thing that we're going to do is we're going to start by addressing underfitting. So if we're both underfitting and overfitting, we'll start with underfitting. Then once we've dealt with underfitting, then we're going to move on to overfitting, and then distribution shift, and then handling overfitting to our validation set by rebalancing data sets if we need to. So to start, let's talk about how to address underfitting. So how do we reduce bias? And here are some strategies that you can use in order that I would recommend thinking about them. So the first thing, the simplest thing, and in many cases the thing that's most likely to be successful, is just make your model bigger, right? So add layers, use more units per layer, and just increase the capacity of your model. You can also consider reducing regularization. So if your model is over-regularized, then that might prevent you from being able to get a tight fit to your data set. You can do error analysis, which is a process that we'll come back to talk about in a few minutes. You can choose a different model architecture, so you can move from your current architecture to something that's closer to state of the art and re-implement that. This can be a very effective strategy. The reason why it's so low on this list is because it can be very time consuming and also can introduce new bugs. So it can cause you to kind of take a few steps back in your process. You can also tune hyperparameters, which again can give you big improvements in performance if you've tried these other things. And then lastly, you can consider adding features. And so in the traditional ML world, adding features is maybe the first thing that you would try. But in the deep learning paradigm, generally, like philosophically, people don't really think about adding features. You want your model to learn the features. But the secret and the trick is that in the real world, sometimes adding features can really help. All right, so let's walk through an example here. So again, our training error was much worse than our goal performance. So the first thing that we might try would be adding more layers to our CompNet. Maybe that reduces our training error to let's say 7%. Still not good enough. So we might switch from a bigger ConfNet to a ResNet, and that might reduce our training error down to 3%. And then we might tune the learning rate. And let's say that for the sake of discussion here, that gets us down to our goal performance of 1% training error. And so now the gap between our training error and our validation error has gotten even bigger. And so the next thing that we're going to need to do is address the fact that we're now overfitting. So some strategies for addressing overfitting. First thing that I would recommend doing if you can do it, or if it's relatively easy to do it, is adding more training data. So I think this is the most principled way to reduce overfitting. In the real world, you don't always have access to more training data. So there's a lot of other strategies that you can try. But if, for example, you're only working with a subset of your data to begin with, then before doing anything else, that would just make your data set a little bit bigger. You can also try adding normalization, like batch norm or layer norm, or data augmentation or regularization. I think Normalization is usually the first thing that I would try. It's kind of like more of a modern approach than regularization. And normalization often also has the effect of reducing underfitting as well. So it can be helpful for both of those things. You can do the same error analysis process that we'll talk about in a few minutes. Choosing a better model architecture can also help you reduce overfitting. In some cases, same with tuning hyperparameters, using early stopping, which some people really recommend using. I have generally not found it to be all that helpful part of my toolkit. Removing features, or lastly, reducing model size. And so I would say I would put these last three things in the like not recommended category. And I think like early stopping might be controversial to put in that category. I think the fast AI folks, for example, recommend using early stopping as part of your regular toolkit. But I personally haven't found it to be that useful. Okay, so let's walk through our example. Again, our training error is good, our validation error is not good. So let's try to reduce overfitting. So the next thing we might do is, remember we were using a subset of our data to make the problem simpler to start. So let's actually increase the amount of data that we're using. Let's say we'll increase it to 250,000 data points. Then we might add a regularizer, like weight decay. We might add some data augmentation. And then, now that our validation error and our training error are relatively close to each other, but no longer close to our goal performance, then we might go back and tune our hyperparameters again. In this case, this time we might tune more than just our learning rate, and this could be the thing that gets us down below our goal performance. Okay, so we have our validation error is down at the goal performance that we originally wanted. The next thing that we'll need to do is address any additional error that's caused by distribution shift. So if there's a difference between the error on our training validation set and our test validation set, then this is the step at which we address that. There's fewer things to try here, which is both good and bad. Good because there's, simpler to pick the one that you want to use. Bad because it's just a harder problem to deal with. The first thing that I would do here is I would look at the errors in your test validation set, and I would look at those errors manually, almost one by one. And then I would try to reason about what are the different causes of the errors that are in our test validation set, but not our train validation set. And I would go and actually try to collect more data to try to compensate for that. And I'll give a more detailed example of this in a second. But when you can do this, I think this is the most principled way to address distribution shift. Again, not always possible to go out and collect more data. So another thing that you can do is, instead of collecting more data to deal with errors in your test validation set, instead you can just synthesize data to deal with those errors. That can often get you pretty far. And then lastly, you can try using domain adaptation as a way of dealing with the difference in the domains. So we talked about this idea of error analysis a few times. Let me give you a more concrete example. So suppose that these are some of the errors that we're seeing in our test validation set and in our train validation set. And these are errors where there is actually a pedestrian in the image, but we're not detecting it. So let's try to reason about what are possible causes of errors in these data sets. So there's one category here that appears in both data sets, which is I would say just really hard to see pedestrians. So I can barely see pedestrians in those images myself at all. There's a second category of errors here, which seems to be related to there being reflections in the images, and that occurs in both data sets. So that's maybe something else we could deal with. And then there's a third category of errors that really only seems to appear in our test validation set, which is images that occur at night, right? So darker images. And so this is maybe one possible cause of error due to distribution shift. And so one way that you can be a little bit more systematic about how you do this error analysis process is you can break down you can look at a bunch of data manually, and you can break down the types of errors that you see, and you can look at how much they contribute to the overall error that you're seeing in your model. So in our case, hard to see pedestrians, let's say that that's pretty rare both in our training validation set and our test validation set. And so it's not a huge contributor to our loss or to our error. And the potential solution here would really be how do we deal with these hard to see pedestrians? Really the main way I can think of is maybe we would have to get better sensors. So this is not a huge contributor to error, and it would also be really hard to fix. So if I did this error analysis process, I would probably make this relatively low priority, at least to start out with. The second error type that we had identified was reflections. And so let's say that this is, a larger contributor to our training validation error and our test validation error. And there's more possible solutions here. So we could try to actually go out and collect more data that has reflections in it and train on that data. We could add synthetic reflections to our training set. So we could use a graphics engine of some kind to try to add reflections to training data that doesn't have it and train the model to perform well on that data. We could try to remove the reflections using some computer vision pre-processing techniques, or we could use better sensors. So if I look at this category, it's relatively large contributor to error both on the train validation and the test validation set. And we have some ideas about how we could deal with it without this really expensive process of adding better sensors. So I might give this like a medium priority. And then lastly, we looked at this error type of nighttime scenes. So very small contributor to error in our training validation set. But let's say that we found a lot more errors that were caused by this in our test validation set. So this is maybe one of our sources of the gap between our training validation error and our test validation error. And some ideas that we could try about how to deal with this. Well, we could actually go send our cars out at night and collect more data then. Maybe that's actually really easy for us to do. Maybe it's not. Maybe that's harder for whatever reason. We could try, and if it is, we could try to create synthetic data to deal with this. So we could synthetically darken our training images to make the daytime images look more like nighttime images. We could try simulating nighttime data from scratch, or this would be a reasonable place to try using domain adaptation techniques to deal with that gap. And so if I was running this error analysis process, I would look at this and say, this is a big contributor of error to our test validation score, and there's a bunch of things that we could try. Some of them might be really easy to deal with it. So I would give this a high priority. And this is probably the thing that I would work on next. Okay, so let's drill in a little bit on this last thing, domain adaptation. So what is domain adaptation? Domain adaptation is a class of techniques that, and there's many techniques that fall in this category, but they generally try to train on some source distribution and then generalize to a target distribution that you want to perform well on using only unlabeled data from the target distribution, or maybe some limited amount of labeled data from the target distribution. And so when should you actually consider using this? If access to labeled data from the test distribution, so the distribution that you want to perform well on ultimately, is limited, but access to relatively similar data is plentiful, and maybe access to unlabeled data from the test distribution is also relatively accessible, then you can consider using domain adaptation techniques. There's a few different types of domain adaptation that you'll see. So there's supervised domain adaptation, where you have, let's say, some limited amount of data from your target domain. And so some examples here are as simple as just like fine-tuning a pre-trained model or adding the data from your target distribution to your training set. But there's more complicated techniques here as well. And then there's unsupervised domain adaptation, where you have, like, let's say, a lot of unlabeled data from your target distribution, but no labels, or a very, very limited number of labels. So here are some techniques that you might see if you look into this. And practically speaking, I would say that these supervised domain adaptation techniques, fine-tuning being the most common, actually work really well. And so this is a thing that's definitely worth considering if you have plentiful data in one domain and then limited labels in another domain. The unsupervised domain adaptation techniques, I think, are kind of more in the research realm than they are actually practical for real-world machine learning systems right now. But it's a pretty active area of research, and so this might no longer be true in a year or two. Okay, so we've addressed our distribution shift, and the last thing that we need to do is consider rebalancing our data sets. So if our test validation score is significantly better than our performance on our actual holdout test distribution, then that means that at some point we ran too many experiments and we overfit to our validation set. And so this happens a lot if you're using a really small validation set, or if you're doing a ton of hyperparameter tuning. And the only thing really to know here is that, if this does happen when you periodically check your scores on your held out test set, then just recollect your validation data or resample it from your test distribution. Okay, so we've talked about techniques for improving model performance. All right, next thing we're going to talk about is the very fun topic of tuning hyperparameters. So let's talk about what hyperparameters we actually have available to us in this problem, this very, very simple toy example that we're using throughout this lecture. So our model architecture at this point is a ResNet. So there's a few different things that we could tune here. We could tune the number of layers, we could pick a different weight initialization scheme, we could change the kernel size or other kind of model specific parameters. We're using Atom Optimizer. We could change the batch size, we could change the learning rate, we could change the Atom specific hyperparameters, regularization, there's many different regularizers we can choose. And so I think like kind of one of the core challenges in doing hyperparameter optimization is just there's so many different things that you could tune. How do you even pick which hyperparameters you should be optimizing? So a few things to note here. One is that, like, for better and for worse, models tend to be more sensitive to some hyperparameters than they are to others. So there's more bang for your buck, in generally speaking, in tuning some of your hyperparameters than other hyperparameters. Unfortunately, which hyperparameters your model is most sensitive to depends on a lot of things, including the choice of model, the choice of data set, and the other hyperparameters that you're tuning. So that's the bad news. The good news is that there are certain rules of thumb that, like, if you're working on a new problem, that you can use to think about, like, okay, which hyperparameters should I try to tune first? And so these are really like only rules of thumb. They, in general, like there's no substitute for building intuition for your problem about which hyperparameters your model seems to be sensitive to. And then the last thing I'll note here is that I'm going to have a prioritized list of hyperparameters on the right, and the sensitivity that we talk about here is relative to default values. So if you're using sensible defaults already, then that gets you a large part of the way there for some hyperparameters. But if, for example, you're using like all zero weight initialization, right, or vanilla SGD, like something crazy, then changing to the defaults, like changing to the standard defaults, will almost always make a big difference. Okay, so let's talk through some hyperparameters. So I think almost always the first thing that's worth tuning is the learning rate. Generally, usually pretty sensitive to the learning rate, even if you're using something like Atom. Learning rate schedule can also be a good one to tune. I think optimizer choice beyond Atom can make a difference, but in my experience is usually not really worth playing around with too much until you're trying to push the limits of your model performance. You can try tuning other optimizer parameters like beta 1 for Atom. I think unless they're like someone else tuned them in a paper and they told you that it depends on this particular choice of beta 1, then usually wouldn't really mess around with this too much. I haven't found it to make that big a difference, although some people say that it makes a big difference for some problems. Batch size, I would say generally is not really like a great thing to tune. I would just generally pick the biggest batch size that you can while still fitting on your GPU. Weight initialization can be a way to improve model performance. Not always, and not really the first thing that I would pick, but if you're having trouble getting into better performance, then playing around with weight initialization is worth doing. Picking a different loss function can have a big impact on model performance. Tuning the depth of the model can sometimes have an impact. Layer size is increasing the width of a layer can be a good one. Playing around with the kernel size and other parameters of layers, sometimes weight regularization, sometimes. And then I would say choice of nonlinearity, so like moving from rel use to some other type of lose, cell use, or anything like that. Occasionally, but usually not. Okay, so this is kind of some rules of thumb that you can use to pick which hyperparameters you want to tune. Next thing that we'll talk about is techniques that you can use for actually tuning them. So the first thing that you'll probably end up trying is just manual hyperparameter optimization. So this is also maybe better known by its colloquial term, which is graduate student descent. So how does manual hyperparameter optimization work? Well, the first thing you do is try to like really think, sit and you stare at the paper and you think really hard about the algorithm that you're implementing. So what does it mean if we have a higher learning rate? Generally speaking, that'll mean that like our training will be faster, but it'll be less stable. And for every other hyperparameter that's part of your algorithm, you'll think really hard about what effect that should have. And then you'll train and evaluate your model, and then you'll try to guess, right? You'll use all this intuition that you built from studying math for many, many years and attending great schools and all this stuff, and you'll guess better hyperparameter values and retrain and reevaluate. So I'm kind of poo-pooing this a little bit, but this actually can be a really good technique, and in particular, it can be a really good technique because it can be easily combined with some of the other methods that we'll talk about. So, for example, you'll often find yourself manually selecting ranges of hyperparameters that you want to run some other optimization algorithm over. And really one of the big differences here is that if your goal is like compute efficiency, So get to the best possible performance with the fewest number of training runs, which, in 2021 is generally not really the right goal because compute is becoming cheaper and cheaper. But in some cases it is, like if you're training a massive model, for example, then this technique will usually have like the least compute required to get to a good result. Obviously, the big disadvantages are that it requires you to actually understand the algorithm pretty deeply to do it well, and it's very time consuming. So this can be a reasonable starting point, but is generally not recommended. The second thing that you'll probably try is doing a grid search. And so the way that this works is you can imagine each of the hyperparameters that you're tuning plotted against each other on a grid, and then you will uniformly sample points on that grid that, for each of the hyperparameters that you're optimizing, and then you'll run your training for each point on that grid. Big advantage here is this is just like really simple to implement, and it can work reasonably well. And the results that you get tend to be pretty interpretable. So, you're picking learning rates and other hyperparameters that are nice, round, even numbers that you would be happy to report in a paper. So that can also be like a psychological advantage. Disadvantage is that this is not very efficient, right? So in order to make this work, you need to train on all of the different cross combinations of the hyperparameters that you're tuning. So if you're tuning more than one or two hyperparameters, then this tends to be very inefficient. And then this often requires prior knowledge about parameters to get good results, right? So you need to choose the size of your grid, like the min and max values for each of the hyperparameters that you want to search over. And if you don't do a good job of picking those values, then you might not get good results. Generally, a thing that's slightly better to do than a grid search is to do a random search. And so the way that this works is you still choose a range for each of the hyperparameters that you want to optimize, but instead of sampling like all of the grid points on that range, instead you'll choose like n points that are sampled randomly from that grid. And so you might think like, okay, why would we do this? Like, why would we expect this to be better than grid? And the reason is that empirically, this tends to produce better results than grid search for the same number of runs. And in fact, like sometimes it's significantly better results than grid search, and it's still pretty easy to implement. So disadvantage is that it's less interpretable, right? So you'll get like these like weird looking numbers as the result of your optimization, and that shouldn't really matter for anything, but sometimes it's like nice to be able to say like, oh yeah, my learning rate is 10 to the negative 3, and that's easy to communicate and easy to remember. And then again, you still need to select these ranges, so you still need some prior knowledge about what values of parameters will get you good results. One way to get around this last disadvantage is by doing, instead of just a single random search, instead doing a course-defined random search. So the way that this works is that you start with like a really wide range of parameters, maybe they're even log scaled, and then you run a bunch of training runs, and then you narrow in on the region of best performance. So you select like say the 10 best or the 5 best performing runs, and then you create a new grid around those data points and resample from inside of them. And then you can keep doing this indefinitely. And so the advantage of this is that you can get really good performance doing this, and you can narrow in on like very high performing hyperparameters. And in practice, I think that this is a really commonly used method. Maybe these days, like automatic, like Bayesian hyperparameter optimization techniques are like potentially catching up to this, but this is an easy one to implement and do in practice. Disadvantage is that it can be somewhat manual. So oftentimes there's a little bit of judgment that goes into deciding like what's the exact range of the parameters that I want to sample when I reduce the size of my grid. But other than that, this is like generally what I would really recommend doing in practice. The last thing to be aware of is Bayesian hyperparameter optimization methods. And so there's a lot of kind of like conceptual surface area here, so we won't really be able to do this justice. But at a very high level, the way that this works is you start with some prior estimate of the parameter distributions, and you maintain a probabilistic model of the relationship between the hyperparameter values and model performance. And then you alternate between training models with hyperparameter values that are aimed at maximizing some expected improvement given this probabilistic model that you're maintaining, and then using the results of your training run to update our probabilistic model. So at a very high level, that's the way that a lot of these algorithms work. And here's a blog post that I recommend if you want to actually go into more detail about some Bayesian hyperparameter optimization methods. So big advantage of doing this is that generally, this is like the most efficient and hands-off way of choosing hyperparameters. You can get great results doing this with very little manual effort. Disadvantages are that these techniques can be sort of notoriously difficult to implement yourself from scratch. And there are off-the-shelf tools that help you with this, but they can be difficult to integrate with. So generally speaking, if you're working on a new project and you're implementing things yourself, I wouldn't recommend starting here. But as your project gets more mature, this can be a really good thing to consider. And I think also like as libraries and like training infrastructure that you use off the shelf gets more mature, a lot of these things are starting to have these techniques built in, which reduces some of the disadvantages that we talked about here. Okay, and so to summarize, like we talked about a lot of different ways of optimizing hyperparameters. Recommendation here is if you're just working on a project by yourself or like starting a new project from scratch, I would recommend using course-defined random searches. Great bang for buck. You can get really good performance. You can inject as much grad student dissent into this process as you'd like to. And then as your project and your code base get more mature, I would consider using some of these Bayesian hyperparameter optimization solutions as you kind of narrow in on what exactly your models are going to look like and you want to spend more compute to optimize them. Okay, so wrapping up, what did we cover today? So we talked about troubleshooting neural nets and debugging deep learning models. And the first thing that we observed is that one of the reasons that this is so hard is that for any given degradation and error that you might experience, there's many different competing sources, like possible causes that could create that error or that degradation in performance. And so that's the fundamental reason why debugging and troubleshooting deep learning models is so difficult. So we talked about a technique that you can use to try to, as best you can, train models that are as bug-free as possible. And the technique that we followed is essentially to treat model building as an iterative process, where you start with the simplest possible version of your problem and your model and your data set, and then you gradually layer on complexity one step at a time, informed by your model evaluation process and your judgment about what needs to be done next, so that at each step in that process, you can reevaluate and redebug, and you can isolate sources of error to the extent that's possible. And these are the techniques that we talked about in a little bit more detail for how to go through that process. Okay, last thing I'll leave you with is there's a few resources I would recommend checking out if you want to go deeper on this. Andrew Ng's book, Good Book, Bad Name. There's a Twitter thread, and then actually a follow-up blog post by Andrej Karpathy that covers some of his ideas on this. And then I also liked this other blog post that's listed here. So check these out if you want to learn more. And that is it. Thank you.